Welcome everyone to our meeting, or what is this, March Alberta section meeting. Our speaker today is Dr. Philip Egberts, and he's talking about friction and wear issues in conventional energy extraction infrastructure. Here's the list of our current executive, and always I will mention we do have a few opening positions, so if anyone is interested, please definitely get in contact with us. Our next meeting in April is on fuels, current technology, regulations, and future development, and presented by Kyle Hansen. I'd like to mention that STLE has their annual meeting. They're still holding it. It's just going to be by virtual. So it starts May 17th through May 20th. And the early bird pricing ends March 31st. So if you're interested in attending, I would definitely jump on that while you can save a little bit of money. Here's a list of our websites through our Alberta section. Our previous recordings can be viewed on our YouTube page. Please confirm that you are muted during the presentation. If you have any questions, please note there is a chat and Q&A option that can be found near the bottom of your screen. The members of the executive will be monitoring all questions and will either respond when asked or save your questions for the Q&A section at the end of the presentation. And please note that this presentation is being recorded. As I mentioned, our speaker today is Philip Egberts. He's an associate professor at the University of Calgary. He obtained his PhD from McGill University in Montreal, Canada, and specializing in experimental condensed matter physics in 2011, while completing most of his research at the INM Leibniz Institute for the New Materials in Saarbrücken, Germany. Following his PhD studies, he joined the Karpik Research Group in the Mechanical Engineering and Applied Mechanics Department at the University of Pennsylvania as a Natural Scientist and Engineering Research Council of Canada postdoctoral fellow. He has been an assistant professor at the University of Calgary in the Department of the Mechanical and Manufacturing Engineering since September 2013, where his current focus is on atomic and nanoscale investigation, adhesion, friction, and wear, with the goal of making physical and predictive models of friction and wear. More recently, has been expanding topics to include engineering tribology to improve the surface engineering for automotive applications and examine lubrication and mechanisms for drilling in oil and gas industry. In July 2015, he was appointed as Associate Head Graduate Studies in Mechanical and Manufacturing Engineering and Associate Professor in 2018. From September 2019 until August 2020, he was a visiting professor at the Humboldt Fellow at the University of Hamburg in the Department of Physics. So welcome, Philip. We're excited to hear what you have to share with us today. I'm going to actually stop sharing my screen and you should be able to take over and share your screen now.
Can you all see that? Okay, I'm gonna try my best to watch the chat while I'm talking. I've somewhat practiced at this giving lectures, so I hope I'll get your questions. I talked with Jacqueline last week, and if you have a question during the talk, you're most welcome to answer it or ask it, and then I will try and answer it then, or I'll catch it at the end if I missed your message. So thank you very much for inviting me, everyone on the STLE Alberta section executive. I've been looking forward to giving a talk to you and to meet everyone in the Alberta section. Unfortunately, virtually this time instead of in person. But I'm really looking forward also to sharing some of the recent work that we've been doing in my group, which I think would be most interesting to people in the Alberta section. So I'm going to talk today about the friction and wear issues in conventional energy extraction infrastructure. And most of this work has been conducted in collaboration with industry here in Calgary. And supported by either NSERC grants, contract work, or Alberta Innovates funding. So First off, let's see. I'd like to tell you that most or all of this work has really been done by my students. This was a picture that was taken just before I went to Hamburg, so it's a little bit out of date now, but at least I photoshopped in the people who weren't able to make it to this one picture. And so most of the work, I'm going to just find this laser pointer button here, that you will see today is a result of work from a postdoc in my group, Tender Panda, and a new MN.
Did we lose you, Philip? I will see if I can get a hold of Philip here. Sorry about that, everyone. We'll just give Philip here a minute to. I see you, Philip. You're just muted.
I vanished for a second. Sorry about that.
There.
Is it working still? Can you see my slides? Or
I
no?
don't see your slides.
Okay, let me share the screen again.
We've got to love technology. We all know I have frozen a few times, so.
Yeah, it got scared. Okay, so are we back up and running now?
You're good.
Okay, thank you. Sorry about that. So before I start, I just wanted to tell a little bit about what we do in my group here in Calgary. And so my group works a lot in nanotribology. So about half my students are in this area. And here we're looking more at fundamental mechanisms of friction. So we look at atomic stick split friction. We look at two-dimensional materials like graphene. We're trying also to do dynamic AFM measurements, which is where you shake the AFM cantilever, and we can basically spatially map mechanical stiffness and viscoelastic properties over surfaces with that. And then we also just do nanoscale surface characterization with that. We have an ultra-high vacuum AFM, so we can eliminate the contamination issues that we see when you're really trying to get down to these fundamental issues. We also have an ambient AFM and hopefully soon liquid AFM as well. But I'm not going to talk about those projects today. I'm going to focus on what I call engineering tribology, or tribology experiments or issues that we're looking into that are more relevant to industry. And so what we've done here is we've done projects previously on surface texturing to enhance lubricity. We are going to talk mostly today about erosion, corrosion, and tribal corrosion experiments today. Previously, we have done some work with Secure Energy and Marquise Alliance, or formerly Marquise Alliance, on making a tribometer to measure the friction properties of drilling fluids with more realistic conditions. And where we're going in the future right now is we're trying to look at nanoparticle enhanced lubricants and greases, particularly using nanoclays. And so this is sort of a new area where we're hoping to sort of pioneer the use of nanoclay as a more environmentally friendly nanotechnology. And also a colleague of mine has a startup company now using, or where she's been able to extract nanoclays from tailings and other waste products from drilling and other mining activities. So these are sort of the topics we're going to talk about today in this talk. And so there's probably people that are much more familiar with and other things or conventional energy extraction in Alberta than I am, but yeah, so we've been contacted by a number of companies who have issues with hydraulic fracturing, and I sort of lumped them all together because it makes more sense for a story. But in particular, we've been working with CalFrac Well Services, and they have problems with the steel pipes they use in hydraulic fracturing, that they rust and get pits in them really quickly, and they start leaking. And so just for those who are not familiar, what we fracturing, you pump a fluid through a steel pipe down into the ore or the earth where you want to extract the gas or the energy source, and you use high pressure water that you inject into the soil. Okay, and when you do this, the water contains a slurry, which is basically rocks or sand inside the water. And then also what happens is that the water is recycled. So as it's pumped in to fracture the rock or the shale formation, then some or most of it is recycled in a closed loop. So the amount of rock debris in the water increases as the process continues. The other thing that happens is that the water becomes more and more salty. So these two factors are really contributing to what the issue is that CalFrac's having, is that these pipes are wearing out quickly because you have rocks hitting the edge of the steel, and you have salty water, which causes corrosion. And so just to sort of graphically depict this is my steel pipe, this blue thing here. We have little sand particles, and then as I said, over time we get bigger rock particles in it. And so for example, in CalFrac, they usually use uncoated carbon steel pipes because they're really cheap and they're easy to replace. But the lifetimes they're seeing are not sort of what they're hoping for. And so the other company we worked with, Endurance Technologies, they're seeing the same kind of issues with these steel pipes used in heat exchangers. Also, where the heat exchangers are flowing water that contains some kind of debris and it's salty. So what happens is the slightly acidic pH of the water and the salt in the water causes corrosion. So you get rust formation or scale formation on the inside of your steel pipelines. And then the debris from the shale that you've fracked or that you pumped through comes off, and it hits this rust and basically removes it. It scrapes it off, and then you reform a protective oxide layer on the bare steel. And this process is happening over and over and over again. And so you're basically accelerating the corrosion by rubbing off the protective rust and then reforming it. So it's just corroding the metal very quickly. And so the other thing that can happen is with mechanical stress, so shear stresses, temperature, you can change the rate of corrosion so that it's much faster than you would see maybe if you were just dipping it in a piece of cold water. And so the impact of mechanical stresses in particular is of very interest in the field of tribocorrosion. So solutions that industry has come up with, which possibly you're more familiar than I am, but these are just some examples. Usually what I understand from CalFrac is basically that they just replace the steel really fast. And what you could do though also is you could coat the pipe. So this is the first topic we're going to talk about, using a hard ceramic or some other very hard material. If the hardness is higher, the wear rate goes up or goes down, so it's more wear resistant. And if you make the coating more lubricious, then if you have this particle impingement on it, it's more likely to slide off. And this first topic is what I will talk about, the technology from Endurance Technologies. And then what CalFrac is doing is they put additives or I should have said corrosion additives. So we're having a fight over some with the reviewers over some papers we submitted. So they add friction or corrosion additives to reduce the friction between the steel pipe walls and the debris, and then also corrosion inhibitors to reduce the rate of corrosion of the pipeline steel. And then the last thing that we're playing around with in the lab here is you could use an epoxy coating, which is pretty common in, I think, corrosion science. And so we're looking at how the epoxy coatings might change friction as well between these rock particles in the wall. So the key questions that we're trying to answer in these projects is what works best, coatings or additives. So we haven't directly looked at comparing the two, but that would be a logical sort of question to ask. We also haven't really looked at cost, but you know, there's so much pipe that you need to use in this case. So is it cheaper to coat the pipes and let them last longer, or is it cheaper just to replace them? I think the question that we also don't know is, what is the environmental impact when you do have a leak in one of these pipes where you don't want it to be? The questions we're really looking at is, how do the coatings or the additives actually reduce wear? What mechanism do they enable, basically, while they're when we're adding them into the fracking fluid? The next question also is, if there's a whole bunch of different additives you can add. So let's say you put a corrosion inhibitor and a friction modifier into the fracking fluid. If you combine them, is it better than just having one? It does obviously cost more to put more different kinds of additives in, and so in our minds it might seem better, but is it really? So we looked into this problem, and then figure out which additive works best. And then lastly, where we started looking at this with our drilling fluid machine, but then the economy changed. So can we use lab tests to replicate real world conditions? So how well can we predict, what we're doing here at the university to what is going to happen when you're actually on the drilling site? And so that, I think, would be very interesting to look at in more detail. So we're going to use this lab-based testing methodology for all the coatings and the additives that we're going to look at throughout this talk. So here we use a reciprocating tribometer for those who are unfamiliar with it. We have, sorry?
We have one question here that maybe can go to your prior slide.
Oh, okay.
Can also the increase in chromium content in the steel?
So like for stainless steel?
Or too expensive?
I don't know how to bring up my my chat window. So we did look at stainless steel. We didn't look at different alloys of steel though. So we didn't get that far, and that wasn't the question exactly that the industry partner was looking for, but I mean, it's something we could easily add on top of what we're doing right now. Does that answer the question?
Thank you.
Okay. So we're going to use a reciprocating tribometer. So here in the big gray square or rectangle is the sample of steel. And what we're going to do is we're going to rub a counter surface along the surface of the steel. Here we have a sapphire hemisphere that's 6 millimeters, and then we have a steel post that holds the sapphire hemisphere, and we basically coat it in nail polish so it's not reactive in a corrosive environment. And then we immerse everything in an electrolyte if we're doing corrosion experiments. We've built everything by ourselves, so we can change it or we can modify it to do all kinds of other things. But normally we're looking at the normal forces and the friction forces. We can also measure if there's extreme wear, how far this counter surface goes into the steel substrate, and we can incorporate extra sensors like a potentiostat. We've looked at pipeline steel. So with CalFrac, they actually brought us pipes from the site that haven't been used yet, and they also gave us used ones. We only looked at new ones, and we cut them into pieces to look at in our tribometer. We've also looked at carbon steel and coated steel samples from other partners. And yeah, as I said, we're using a sapphire hemisphere. And in all cases, in case you're wondering, we did not see any wear of the sapphire hemisphere. So the reason why we're using sapphire is that it replicates the chemistry kind of the sandy rocks that are in the pipeline. It's very, very hard, so it doesn't wear out. We can then attribute all the wear to the counter surface, and it's chemically inactive in electrochemical experiments. So that's why we're using this one. We use a 3-probe electrochemical setup. So here we have in pink, the sample. Underneath it, we have the stage that's moving the sample. The counter surface is fixed, and we put a platinum mesh electrode for the counter electrode inside of the solution. We connect the working electrode output to the sample, and we have a reference electrode, which is a silver chloride electrode here. And this is what it looks like in real life. So it looks, it's been improved. Every new student that comes on, they add some more and more pieces to it to make it easier to use or more reliable. And this is one of the earlier pictures of it, but it's basically, we have a pool that we clamp onto the sample so that it's leak proof and can hold the electrolyte. And then we don't move it too fast, so we don't create any tsunamis or wave pool action in the tribometer. So what the outline of the talk then will be on 2 sort of studies that we've done. One of them is looking at the wear corrosion performance of boronized coated steel samples, having low friction top layers, and the sponsor for this project was Endurance Technologies. And then we looked at additive chemistry of hydraulic fracturing fluid for the improvement of wear corrosion performance in pipeline carbon steel. And we performed this with Calfrac Well Services. And then I have some ideas about some future work, but I didn't get those slides in there, and I think we're going to run out of time anyways. So we can just talk about where we're going in the future in this work. So the idea from Endurance Technologies was that you could improve the erosion corrosion performance of steel or other metals by making a boronized layer or coating on top of the steel. And basically what they have is a huge furnace that you can put pipes in of very large sizes that can be put on like 18-wheeler truck, or you can even make a heat exchanger and coat the inside of your heat exchanger with this process. And this process results in an ultra hard coating that is 14 to 20 gigapascals. And iron or borides are in general corrosion resistant. So you enhance the corrosion resistance of the steel. And I think when I saw a talk from them, they said that the resistance is like a factor of 20 improvement in the lifetime of the pieces. They're looking at new processes where they can also put low friction or dry lubricants sort of on the top of the boronized steel. For example, boron nitride, and they play with the chemistry of the boron nitride a little bit so that the friction is even more reduced, and so these particles can slide off even easier. And so the thickness of this top layer, this low friction top layer, is about 5 to 30 micrometers, and then they have this ultra hard coating that's about 150 micrometers below it, and then you have the base steel. In this case, we're looking at carbon steel and stainless steel. We can look at the microstructure of the surface. So here on the left, we have the base steel here. When you do this boronizing process, you get 2 different kinds of iron boride. So one is Fe2B and one is FeB. They have a slightly different microstructure and they have different mechanical properties. And so we have a nano indenter, and so we can track the mechanical properties from the bulk of the substrate all the way to the surface. And what you see here is, here's the carbon steel base layer hardness, and this is the hardness of the stainless steel. So stainless steel is a bit harder, that imparts more wear resistance, but you can see there's a 2-fold factor improvement in hardness from the stainless steel approximately to the boronized steel. And so you really see an enhancement of the wear performance of these coatings from this improved hardness. We did not see, however, in these optical microscopy images, the top layer. So this low friction top layer is not visible in this picture. So we have to look at it in other ways. So the first experiment we performed is looking at how did this material or these coatings perform in dry sliding. So when we did not put any corrosive solution in our tribometer. And so we have all these different samples here, which is slightly confusing. So here, this is the stainless steel sample. CS is for the carbon steel. And so what you see here is the friction coefficient of the stainless steel is really quite bad. These are all different boronized steels, are coatings that have different layers. And so in general, I'll pick out two ones that we should pay attention to. So this one that's labeled BB, basically on the top coating, and then I just got a message that my connection's stable. Can everyone still? Not working. I'll keep going. There's the chat.
You're getting a bit.
Okay. All right. So this boron has a nitriding in it so that it's better, and it was thought that it improved the wear resistance of this coating. And this BB has extra boron in it, in the boron nitride layer, and it is very lubricious, basically. And so basically, Endurance Technologies is really looking at this technology following their own internal experiments in these ones. So carbon steel and stainless steel showed poor performance. The nitrogen rich, or this sort of hardened coating, didn't perform well at all in these dry sliding experiments. And the boron enhanced top layer performed very, very well in dry sliding experiments. And so what we know from these experiments is that the top layer chemistry is very important. So it's not all boronized steels are created equally. What we did then is we put these samples in the corrosive medium. So in this case, we looked at 0.5 molar sodium chloride in deionized water. And what this graph shows you is at the beginning, this is before we start moving the tribometer, and then all of a sudden we start sliding the experiment back and forth. And we see a change in the working electrode potential that we measure in our 3 probe measurements. And then we stop the experiment here, and we see that the working electrode potential goes to a more or less negative value. And so we do this because we want to wait for basically an oxide to form. So you see particularly this green line arcs down to sort of a constant value here, and we wait for that to happen before we start the experiment. And what we see here is that the more or the less negative the working electrode potential is, the less likely this material is to corrode. So we see here that the stainless steel performs the best, and the carbon steel performs the worst, okay? Which is obvious to most corrosion scientists here. And the boronized steels they have a more positive value than the carbon steel, but they have a less or more negative value than the stainless steel. So they're not as corrosion resistant as the stainless steel, but they're better than the carbon steel. And we see that these boronized steels basically or essentially have very similar corrosion potentials compared to each other, okay? And we also see that the shear stress or the rubbing action of the tribometer significantly alters the corrosion potential. So when we start rubbing back and forth, we see that everything starts corroding a lot more than it was before we started the experiment. And so this is sort of the issue that why the pipes are wearing out so much in these hydraulic fracturing applications. And then we so we can also measure the friction coefficient while we're doing these corrosion measurements, and we see here that now the friction coefficient of the carbon steel increased significantly, and we see very low friction in these electrolytes of the boronized steel. And we still see that this boron enhanced top layer is really performing a lot better than all of the other coatings. We measured the wear rate. So basically what we do here is we take a picture of the groove, and we over a certain area, and we calculate the Archer wear coefficient, and we compare the wear rates when it's in the corrosive medium, which is on the hatched one on the left, versus the sorry, this is the corrosive medium, and this is the dry slotting. So I'm just looking at this picture from Zoe. How is the corrosion measured here? So we're using, in this case, what we're doing is we're measuring the working electrode potential as a free parameter. Like, we're not applying any potential to the sample, and we're measuring the working electrode potential while it's immersed in the bath. And then all we're doing here, when we change when I say we start sliding or we stop sliding, essentially we just press the tip in, we wait for time, and then we start sliding back and forth. And we're recording simultaneously the potentials and the currents with the potentiostat while we're measuring the forces, if that answers the question properly. Right, so again, when we compare the wear rates here, the boron enhanced top layer performs the best of all the different samples, and in both dry sliding and in the electrolyte. And the carbon steel performed the worst, which is sort of obvious from what we know about carbon steel. And in general, though, all boronized top layers did pretty good for their low wear rates. This is an example. It's a little bit complicated to understand this graph, but essentially this point here is where the surface was, we have wear coming down to this dotted line. So this is where the top layer would be, where the boronized steel starts, and this is where it was worn to, and this is the top layer thickness. And so what I'm trying to show here is that all the top layers, except for the BB and the BN samples, were removed over the course of these experiments. So this enhanced boronized top layer survived both the corrosion and the rubbing action from the tribometer itself. In the other cases of these boronized steels here, the top layer was completely removed, and we were wearing out the boronized FEB, FE2B coatings. Okay, and so this really shows then that this enhanced boronized steel or boronized top layer would be important to use if you wanted to ensure that you had this lubricious top layer. What we'll show later is that the long-term friction performance is really dictated by the tribofilm or the chemistry of the worn material, the electrolyte, and the boronized steel below it. We looked at the surfaces in both optical microscopy and electron microscopy, and I'm just going to pick out two quick examples here. Here we have this nitrogen enhanced boron top, or hexagonal boron nitride top layer. That's the harder coating that didn't perform as well. And what we see here is delamination of the coating. You can see the underlying steel substrate here. And this latter stuff is the top layer. And if you compare this to this enhanced or boron enhanced top layer, what you see is you don't see this removal of the top layer. You can't see into the substrate, and you see this sort of plate formation in the wear track itself. And so this is what's really providing this lubricious friction coefficient that we measured in our experiments. So the idea or our proposed mechanism is that when we put the steel, this is the counter surface, the electrolyte, the steel, and the sort of stage that's moving back and forth. When we put this in with the steel and the electrolyte, we form a rust or a scale on top of the steel, and then we rub the counter surface back and forth, and we basically tear off the coating. We form wear particles, which are hard, and then this in turn starts removing more and more material. We also have corrosion happening of the steel at the same time. When we have this boronized layer on it, we don't form the wear particles that we would in the carbon steel sample, and especially when we have the lubricious top layers, and so we can maintain the thickness of this protective layer on the steel. So just to sort of wrap up this project, the boronized steel is very effective for improving the wear performance of the steel compared to carbon steel. The top layer chemistry is really important for reducing friction and corrosion performance. And then we did use very high contact, or this should be contact pressures. So it's in the gigapascals range. So likely the impingement of the rocks or debris in the pipeline is not going to have such high pressures. But we can show that the lifetime is significantly increased when we use this boronized steel because we did use these high pressures. So moving on to the second topic I wanted to talk about is looking at hydraulic fracturing fluids. And so what we did is we cut pieces from the pipeline steels that they were using on the fracking site. We compared deionized water to high TDS. So this is total dissolved solids. This is the fluid that they basically took from the site in giant buckets and brought it to the lab. So it has all the rocks and stuff in it. And then we tested 3 corrosion inhibitors. So we looked at an organic corrosion inhibitor. There was one high molecular weight and one low molecular weight one here. So Dynarate is high molecular weight, DWP is low molecular weight. These are the trade names of the additives they're looking at. And we used an inorganic corrosion inhibitor, which is called CalGuard, and this is basically an oxygen scavenger to reduce the oxygen concentration in the fluid. So we first looked at we compare D means distilled water, T means high TDS water, and then the subscripts here mean the additives that we tested. So we tested distilled water here in blue. It had the least amount of corrosion, or is the least amount or most resistant solution to corrosion. Then we tested the steel in the high TDS water, this T, which is down here at the back. It's the most corrosive solution. And then when we added it, we put the different additives in, they did what they were supposed to. So they changed the potential, and so it's less corrosive as you add these different chemicals in. And in this case, we looked at adding both the 2 organic friction modifiers at the same time. And when you see C here, we added the CalGuard and one of the friction modifiers as well. Right, so DWP has more impact on the corrosion potential compared to the other 2 corrosion modifiers. But we'll see later on that some interesting results with the friction testing. And so here's the friction coefficient versus the cycle number here. And you see that there's very high friction with this salty water. And this is because we're ripping off all these wear particles from the steel. When we use the DWC, which is the DWP plus the corrosion inhibitor, then we see also a high friction coefficient. And then when we add the other additives and the distilled water, we see much lower friction coefficient. So in this case, Dynarate rather than DWP performed the best. And we didn't really see that if you mix 2 different kinds of additives together, there wasn't really a change in the friction coefficient. So while DWP performed the best for reducing corrosion in terms of the potential, Dynarate performed better for reducing the friction coefficient. So what do we do now? We have all these parameters. So we want to figure out what's corrosion and what's wear, and how the corrosion and wear might be acting synergistically together. So we extrapolate corrosion rates from the Tafel slope of the potential versus polarization density. In stage 1, we measure the wear loss at an open circuit potential in reciprocation experiments. And then we apply basically what I mean, this is my bad corrosion scientist, so Zoe, I'm sorry. we apply cathodic protection. This was sort of my application here to stop corrosion. So we apply -1 volts to the sample. And so basically we have only mechanical wear happening on the sample. And then what we do is we look at the total wear of the experiment. And then we make a combination of the total wear equaling the taffel slope from only corrosion, the cathodic protection potential, which only looks at mechanical wear, and then the remainder between the total wear and these two parameters is the synergism, or the interaction of corrosion and wear to accelerate the wearing out of the pipeline steels. And so what we see is when we apply this -1 volt to the sample, we really change the friction coefficient. So if you remember, the TDS water really increased the friction coefficient a lot higher, and these values are similar to what for the other additives, very similar to what they were before. And so the corrosion is really impacting the friction behavior. So we also did this polarization measurement, so we can see here the impact of the different additives on the corrosion potential, and then you can measure the taffel slope from these curves here to figure out what the weight loss is per year, essentially just from corrosion. And then this graph here tells us essentially the total wear of the system. This is the wear due to corrosion, and this is the wear due to the mechanical sliding of the sample. And so, for example, here you see that there's a great synergism between corrosion and wear, or mechanical wear, because this teensy tiny little corrosive loss versus the wear loss when there is no corrosion is much smaller than this blue curve. Okay, and so what you can do here is there is significant synergism for all examples here, except for this deionized water, when you add these different additives into the surface. And so this makes understanding, what's going on in your system very interesting. In all cases, though, mechanical wear, again, we used very high loads compared to what would likely be experienced on site. We show that mechanical wear is really high with these high loads. And there is significant enhancement of corrosion and wear when you combine the two in our tribometer. Okay, we also see that when we mix the additives together, there wasn't such a huge increase in the performance. So if you see here this dyno rate here, wear rate compared to the DWR2, when you add the two additives together, it actually performed worse with two additives than just with the one. So mixing additives in our study didn't show any sort of synergism between the different additives. We looked at the corrosion mechanism in the high TDS water without or away from the worn areas, and we saw that pitting formation was the likely mechanism of corrosion in these two in these cases. And so basically, I'm skipping over a bunch of things that we looked at, but what we think is happening is we add these organic friction modifiers. And when we have these organic friction modifiers, they sort of form these like groups on the surface. They adsorb on the surface, and with the higher molecular weight, we see absorption on both the counter surface and the substrate, which really reduces our friction coefficient and wear rates. Do you compare the lab erosion field data? We don't have any field data from the piping. Basically, the economy got really bad when we got all these results, and so everyone vanished, and we haven't really had a chance to look at field data. So I don't know. I don't know what the lab data would show. Right. So so we think that dyno rate is sticking to both the counter surface and the substrate compared to DWP, and that's why we're seeing this sort of benefit from this additive. So to summarize this thing, we see that organic friction reducers are more effective at reducing wear corrosion than the inorganic additives. We looked at the mechanism, and mixing the additives didn't really show any impact on the wear, friction, or corrosion rates. Just a quick note, because I know I'm running out of time here. We also started looking at doing a statistical analysis of the wear rate, or the impact of the different additives on the wear rate, the friction coefficient, and the corrosion. And when we did this, we saw that basically the more you increase the dyno rate, the better everything got. So we only went up to 1 volume percent, but somewhere around 1 volume percent is around where you would hit the solubility limit of that additive. And we did this statistical regression on these different parameters based on the concentration of the additives. And we confirmed that also there's no real synergism when you use multiple additives. And yeah, as I said before, dyno rate is the best additive here. And so just to summarize the whole idea of the talk, we did friction and wear testing of pipeline steels and with different coatings and additives, and we can look at mechanistic ways that these additives or coatings are changing corrosion and friction, and this is really important for the development of the various technologies. We also do this reciprocation measurements, which are not the standard tests done for erosion, corrosion. We don't do impingement testing, for example, but we can get a wealth of information out of this kind of testing that you can't get from impingement testing. And we did, so this, I didn't show this graph, this is our statistical analysis. We use this analysis to sort of deconvolve complex additive packages to see which additives are working better than other ones, and then this could be sort of used to optimize the concentration of your additive package, or remove things that aren't unnecessary and costly. And what we're hoping to do in the future is to use this kind of statistical analysis to get one step further and look at it like in terms of using machine learning or artificial intelligence to train the computer to sort of guess where we should do our experiments next. This is a technology that's just starting to get popular. You've been hearing it in the news a lot, but it's really slow to be embraced by the tribology community. And we're really excited to look at how we can use these computational techniques to sort of guess what the mechanisms are, or help us make our experiments more efficient. I'd like to acknowledge, as I said, funding from Alberta Innovates and NSERC. Endurance Technologies, Eugene Medvedovsky was really helpful in getting us up to speed on the boronizing steel technology. Calfrac Well Services funded all of this work on the hydraulic fracturing fluids, and I have a grant from Transport Canada to look at these nanoparticle enhanced lubricants, and this allowed us to have Jitendra come and visit our lab, and he's been instrumental in getting these results, so I'd like to acknowledge funding from there. So that's all I have to talk about today. If you have any questions, I would be happy to take them.
Thank you, Philip. That was really good. I will leave it open for just a few minutes here to see if any questions are typed in. I know you answered a few during. And I will make sure that you and Zoe are connected as well.
Oh, Zoe's a friend of mine, so I sent her the link to come today, so I have her email.
Oh, perfect. So if there's any questions, oh, here comes one. Jackson, if a company could only afford to implement coatings or additives, which do you think would have a greater impact on increasing the time to replacement? So
I guess the answer to the question, I didn't really specify this, and I think everyone who works in the industry sort of knows this beforehand. The additives are a lot cheaper to use, even though you have to use a lot of them. DWP is less expensive than the dyno rate because of the molecular length. And so Calfrac was using this as sort of their efficient way to make the pipelines last longer. The coatings, the boronizing process is, I gather, somewhat a lot more expensive than just carbon steel. And so the hurdle that Endurance Technologies is dealing with is trying to show the industry users why they should adopt this technology despite the high upfront costs in capital for using these pipes instead of a carbon steel pipe and replacing it all the time. And so the boronized steel lasts way longer than the coatings, but it's also more expensive than using the additives, I think. I'm mean, I haven't actually seen the prices, but this is what I heard from Eugene and from CalFrac.
Okay, thank you. I'll give it another second. I do want to acknowledge that SAE has been joining us and is partnering with us. They have been sharing our speakers with their people, and we're sharing their speakers with ours as well. So just like to acknowledge them as well. I don't see any other questions, so I will call us to an end. And then just again, thank you so much, Philip, for presenting. And yeah, we'll be in touch.
Thank you so much for having me.
Thank you, everyone. Have a great day.